Welcome everyone to a video tutorial on how to solve a simple weak acid equilibrium or a Ka problem. In this example, I'm going to show you how to solve for the pH of a weak acid solution. There is some prior learning that goes into understanding how to solve this problem. So first of all, you should have already been introduced to the equilibrium law and to be able to solve simple equilibrium problems using the equilibrium law expression. Second, you should be able to write out acid ionization equations and identify the Bronsted-Lowry acids and bases in a chemical reaction. So let's look at the problem. In this example, we want to determine the pH of a 1.5 times 10 to the negative 2 mole per liter acetic acid solution. And the Ka value for acetic acid is 1.8 times 10 to the negative 5. Let's switch over to the whiteboard and go through the steps on how to solve this problem. The first step in an acid-base equilibrium problem is to write out the acid or the base ionization equation. So in this case, we're dealing with acetic acid. So let's write out the acid ionization equation for acetic acid. As in previous examples in this unit, I'm going to use the short form AC to represent the acetate ion, and on the left here, HAC represents acetic acid. Let's now build an ice table and input the information that was given in the question. When we're given a concentration of a weak acid, that is given to us as the initial concentration of the unionized acid. So we start off our ice table with that concentration given to us as the initial concentration of the unionized acid, and we have no ionized acetate ions or hydronium ions to start. And as with all equilibrium problems, we're interested in figuring out to what extent this reaction is going to proceed. We're in a 1-to-1 ratio, so for every X moles per liter of the acetic acid molecule which ionizes, we will produce X moles of hydronium ions and X moles of acetate ions. And so at equilibrium, we have the following concentrations. Our next step, as with all equilibrium problems, is to write out the equilibrium law expression and then substitute in our equilibrium concentrations from our ice table. Here is my equilibrium law expression. Remembering the Ka expression is going to have the hydronium ion and the conjugate base on the numerator, and then we have our weak acid on the denominator. Then I'm substituting in my equilibrium concentrations into the equation. As with all equilibrium problems, our next step is to solve for X. At this point, we are going to do a bit of a simplification. And this simplification can be done if the initial concentration of the acid is quite large relative to the change. Let's focus in on the denominator here. If the value of X is very, very small relative to the initial concentration, which I've underlined here, then we could probably treat that as a rounding error. For example, if 1.5 times 10 to the negative 2 minus X gives us something like 1.50004 times 10 to the negative 2, if you got that value as an answer, you'd probably look at that and just round that off to 1.5. So even though there is a change relative to the initial concentration, it's simply a rounding error. It's insignificant. We can make this simplification generally if the initial concentration of the acid is a factor of 100 or more times greater than the Ka value, which I've underlined as well. So 10 to the power of 2 or greater. If you notice that difference, it is probably safe to make this assumption. So let's write this out formally. What we're actually going to do here is make an assumption that the percent ionization is less than 5%. And if it's less than 5%, then we can assume that the initial concentration minus the change, 1.5 times 10 to the negative 2 minus x, is going to be approximately equal to 1.5 times 10 to the negative 2. And so as I've done in the next line, I'm going to simplify the denominator. Note that we are not saying that x is insignificant. We're just saying that relative to the initial concentration, it is a very insignificant change. At this point here, we can now rearrange the equation and solve for x. When I rearrange and then take the square root, I get the x value to be 5.2 times 10 to the negative 4 moles per liter, which is my hydrogen ion concentration. At this point, before proceeding, I do need to check to make sure that the assumption was valid. The way we're going to check it is we're going to check the percent ionization. If the percent ionization is less than 5%, the assumption is valid and we can use this. If the percent ionization is greater than 5%, then we're going to need to go back to before we made the assumption and solve for x, likely using the quadratic formula. So let's check that now. In order to verify, we'll plug in our equilibrium concentration of the hydrogen ion, which we just calculated, and divide that by the initial concentration of the acid, multiplying by 100% to express it as a percentage. And we find that in this case, the percent ionization is 3.5, so it's indeed less than 5%, and that means that our assumption that we made is valid. Our final step in this problem is to use the pH formula to, starting in 3, 2, our final step, starting in 3, 2, our final step in this problem is to use the pH equation to solve for pH using our hydrogen ion concentration. We find our pH to be 3.28. You will see that many problems involving acids and bases, even the ones where we're applying them in different situations involving buffers or titrations, use the same general format here. And in most cases, we're able to make this assumption to greatly simplify the process of solving for our hydrogen ion or hydroxide ion concentrations.